Okay, guys, so day one we started out factoring, and then day two we did long division and synthetic division. The purpose of long division and synthetic division is to help us with factoring. We're going to elaborate on that a little bit more in lessons to come. But for now, I want to show you one of the uses of factoring. One of the purposes of factoring is to help us solve equations, okay? So let's go ahead and begin. So I've got a lot of side conversations going on out there. Rami, Josh, we can have no talking now because I'm teaching. No problem. All right, here we go. So roots of a polynomial. So roots of a polynomial are also known as the x-intercepts, where the graph touches the x-axis. Okay. Now the significant thing there is that that's where the y value equals what? 0. Okay, I'll get you one in just a second. So that's where the y value equals 0. Now the way we're going to go about finding the roots today is it's a two-step process, but it's going to be like a three-step process kind of. But we're going to factor it, and then we're going to use something called the zero product property. Okay? Yep. A lot of this will be reviewed for you guys, but it's a good thing to review because it's probably been a while. Why do we care about the roots? Well, basically, this is how you solve equations. This is how you graph. So this is all that stuff kind of comes into play when you're working with polynomials. All right, so go ahead and copy down example 1, please. I want to find the roots, which is another fancy word for x-intercept, which means that's where it touches the x-axis. And when we're on the x-axis, what's the y value? 0. So that's step 1, the easiest step of the day. It's just to replace the y with 0. So let's write that first. Plug in 0 for y. Okay? Now the next thing we're going to do, and it may not seem evident why we're going to do this, but I'll explain why in a minute. But the next thing we're going to do is we're going to factor this thing as much as possible. Now a few days back I gave you guys a little chart. It looks something like this. You always start by looking for a GCF, right? If there's two terms, then you use the difference of squares. You remember that? Yeah. You don't need to rewrite this. I'm just writing it to illustrate what I'm talking about. 3 terms, we use the box. 4 terms, we use the box. Okay? So we always start by looking for a GCF, and then based on how many numbers there are, we do one of these 3 things here, okay? Or one of these 2. All right, so let's start by looking for a GCF. Is there anything that divides into 2 and 162? 2 does, so let's go ahead and put a 2 out there. Also, do they both have x's?
Yes.
How many can I take out?
Oh, no.
Only 1. So I'm going to divide both of these by 2x to find out what's left on the inside.
1.
So on the front we would have 1. How many x's though?
4.
4 of them. 1x to the 4th. And then minus 162 divided by 2 is 81. And x divided by x is 1, but we'll just kind of cross it off and say that's done. Okay? So that's the first thing, is you look for the GCF. Then what do? Difference of squares or box? Good, because it's got 2 terms, right? So we do the difference of squares. So, don't forget your equals 0. Here we go.
Hey, did you put a 1 in front of x?
Yeah, you don't have to. Okay, so this thing is going to split up. How do you do the difference of squares? Well, you take the square root of that, which is? Good. And you take the square root of that, which is 9. You make one a and the other a negative. Now, we've got to keep going if we can. So this is done. Is this anything? Well, if it's anything, it would be a difference of squares because it's got 2 terms. Is that a difference of squares?
No.
Not quite. There's something wrong. What is
Not
it?
a negative.
It's got to be minus. So that's not a difference of squares. That one's done. How about the next one?
Yes.
Yes.
That is a difference of squares, so let's keep going on that one. We have x minus 3 and x plus 3. Okay, so that's the end, because now neither one of these are difference of squares and we're done. So let's go ahead and draw another arrow here, and we'll say factor completely.
That's the final.
No, not yet, but we're almost at the final step. So, step 1, plug 0 in for y. Step 2, factor it completely. Now, those first two steps, we're going to use those two things together to solve for x now. And here's the fact that we're going to use. We're going to use something called the zero product property. You don't need to write what I'm about ready to write, but I just want you guys to pay attention and understand it. If I tell you that a times b equals 0, what do we know about a and b?
There's 0.
One of them has to be 0, or maybe both, right? That only works when you have two things that are being multiplied and equal to 0. That doesn't work for anything else. Like if I did this, a times b equals 1. That could be, there's an infinite number of things that could work for that. Like if this was 2 and this was a half, that works. How about -1, -1? That works. But when it comes to a times b equals 0, there's literally only one possibility. Those things have to be 0, right? So you can't solve this one because there's too many possibilities. But you can solve the first one. So check this out. Step 1 gives me the 0. Step 2 changes it from being adding and subtracting into a whole bunch of multiplication. And now I can use the zero product property to solve for my unknown variable, right? So let's go ahead and write down step, whatever that was, 3. Okay, so here we go. So if all these things, if this times this times this times this equals 0, that means that either this equals 0, right? Or this equals 0, or this equals 0, or this equals 0. This is what's known as the zero product property. And now can we solve for x to figure out what x would be? Huh? Sure. So you just take each piece and set them equal to 0. I'm not saying anything new. So so Josh, if these four things multiply together to make 0, that means one of them has to equal 0, because when you multiply and you get a 0, one of those things has to be 0. So let's go ahead and solve these. If I solve this, what would I get? 0. So let's box that. That's one of my roots. That's one of the places where my polynomial would touch the x-axis. Okay? Let's do, I'm going to skip this one. I'll come back to that in a minute. Let's do this one. Plus 3, x equals 3. There's another place where my polynomial touches the x-axis. Finally, we have this one. Well, not finally. We are going to go back and do the other one. We have that as well, right? Let's come back to the guy in the middle here, though, because something kind of weird happens here. So, first of all, we're going to minus our 9, right? Square root. Good. Do you guys remember what you have to do when you solve by taking a square root? That's true, but before that, you get a plus minus. Okay? When you solve an equation by taking a square root, you always get a plus minus. Now, Rami pointed something else out, the fact that, I think it was Rami, when there's a negative on the inside, you do need to take out your I, right? And then what's the square root of 9? So here's our final answer. Now, what this means is that this is an imaginary root, and it doesn't really touch the x-axis there. There's no, this doesn't exist, right? Doesn't touch x-axis. So this polynomial really only touches the x-axis in 3 places, but how many roots are there altogether? Let's see, because this is kind of significant and worth noting. 1, 2, 3, and how many are here? 2 more, so a total of how many? 5 roots. So I want you guys to take note of something. I have 5 roots. right? 2 of them are imaginary, but I still have 5 roots, correct? Let's go back to the original problem. See that power right there? That's how many roots you should end up with technically, okay? So whatever that power is, when you're breaking this down, you should end up with that many factors and therefore that many roots, okay? So, you know, you could write a little note here. We should end up with 5 roots. Now, here's the thing. You might not be able to find all those roots, okay? Especially using the method I'm sharing with you today. Now, in the days to come, I'm going to show you a few more strategies to find other roots. But all the roots that we just found today are nice numbers. But they could come out to be weird numbers that are like really funky decimals or frac or something like that. We're going to look at those. You also have imaginary roots. We saw that come up. By the way, it's also possible that when you factor something, you get the same factor twice, right? And if that happens, you get the same root twice. Now that still counts as 2 of them, but it's really just 1 root, right? So it's possible then technically, like if I gave you guys this, x to the 5th equals 0, you can say there's 5 roots, but they're all 0. 0, 0, 0, 0, 0. Got me? So, but that's how you solve a polynomial or equation, or how you find its roots. Plug in 0, factor, solve. So let's go ahead and do one of these real quick here. Yep, let's do number 1. Go ahead and write down number 1. I have a typo here. Can we change this to a minus 3x, you guys? Otherwise, it won't actually factor. So change that to a minus 3x. Box. Jordan, what did you factor it into? Okay, there you go. That's correct. Now I want you guys to do the next step. The next step is to solve for x using the 0 product property. You take each piece, set them equal to 0, and solve. One of them should give you some imaginary answers. The other one will give you a real one. Go ahead and see if you can find your roots. I'm going to pause here. And if you don't know how we got these, I'm going to write that on the side. But if you do know, then we're going to practice factoring tomorrow. So if you're feeling a little rusty with the factoring, you'll get a chance to refine that tomorrow, okay?
Thanks, man.
You're welcome.
Why are we covering factoring?
Because you need the review.
We need a whole week.
Right.
All right. Now, I don't want you guys to write this, but I would like you guys to watch. The bell means be quiet. It means don't finish your conversation. Stop right in the middle of the sentence and then stop talking, okay? Okay, so I don't want you to write this. I want you guys just to watch, okay? So here we go. I want to find the root. So the first thing I do is I set it equals 0. Second thing I do is I factor it. Third thing I do is use a 0 product property and solve for x. Now, I want to track these numbers. And as I track these numbers, we're going to come up with an interesting shortcut to find the roots. Although it's not necessarily a shortcut. It's actually just another way to find roots, which is kind of helpful when factoring fails, because sometimes factoring will fail us. Okay, so here it is. Take note of this 5. Where was that before this step? Yeah, there, right? And then there. How about this 1? Where was that? It was here. Where'd that 1 come from? Came from this, right? And that came from here, right? Now I'm going to change colors, and that's on purpose. So, how about this 3? You guys see where that 3 came from?
Yes.
Right there?
Yes.
Which came from?
There.
Here.
Yes.
You see this too?
Yes.
Okay, now, this isn't a coincidence. This is something I want you guys to notice. First of all, The 3 and the 2, what do they have to do with this thing up here?
That's what I don't know. If you multiply them, they factors to.
They come from the 6x squared. You guys see that? How about the 1 and the 5? Where do they go to? They come from there. So here's what I want you guys to know is I'm gonna erase a lot of stuff now. Let me. So the 3 and the 2 come from here. Wrong color. And then the 5 and the 1 come from here, right? So now I'm going to erase all this other stuff because it's kind of just getting in the way of our shortcut. But it helped us get there. So here's what we got then. In our roots, the numerators come from the factors of the last term. And our denominators come from the factors of the first coefficient. Okay? So we have a shortcut now to figure out roots. Here it is. Let's say that I did not have any idea about how to factor, although we do. But let's just pretend for a second that I don't. How can I find the roots in another way? Well, what we just learned is, what are the factors of the last number? What times what makes 5? What times what makes, I'll put L here for last. What are the factors of the first coefficient? 4, 1, and 6. So, and I know that the roots will have these numbers on the top and these numbers on the bottom. So here are my possible roots. My roots could be 5 over 1, 5 over 2, 5 over 3, or 5 over 6. Or they could be 1 over 1, 1 over 2, 1 over 3, or 1 over 6. So I've got 8 possibilities there, okay? And it just so happens that we don't really know the signs either, right? They could be positive or negative. We didn't talk about that. But what were my 2 roots? Wasn't it 5 halves and a half or something like that? So it's one of them. So now we have a way to kind of know our roots without actually factoring. And why is that important? I wouldn't do this for this problem. I would just factor. But there are some polynomials that we have no factoring strategies for. So this is the way we're going to have to do it. Okay? So what we do is we take the factors of the last, factors of the first, and we make fractions. Now here's the thing. How do you know which ones are correct? Well, we can figure it out. These are the what of that polynomial? Those answers are called the roots, okay? Now roots make the y value what? 0. So if I plug this number in, it should equal 0. That's how you know which ones are the roots. So you're going to make a list of all your possibilities, and you're going to plug them in until you find the ones that give you 0, and you've got your answer. Yeah, and we're going to be using calculators for that. So if you guys want to go grab a calculator real quick, a blue one, you can use a yellow one too, that's fine. So downside number 1 is it's tedious. Downside number 2 is it only helps you find rational roots. Rational roots are things like 5 is a rational root, or 2/3, because rational means fraction, and both of those are fractions. Okay? But if you end up having like a root like this, or a root like this theorem will not get you those roots. You have to use other strategies to get those kinds of roots. Okay? So, let's go ahead and begin. So remember, after we do this little step, it only tells you the possible roots. It doesn't tell you what the actual roots are. So how do we know what the actual roots are? We talked about it already. We're going to plug them in, and if they make it equal 0, then that's an actual root. Okay? So, let's do one here. Go ahead and write down example 2. Now, some of you guys are using cell phones as calculators or Casios. Not all Casios, but those ones don't work as well. You want to have the kinds of calculators that as you type it in, it shows you what you're typing in as you go all at once. Not the ones where you have to do a step one at a time, because that makes it kind of hard. It'll work, it's just tedious. Tedious means a lot of work.
All of these problems are a lot of work.
It's like, because it's tedious. This is a tedious problem. All right, here we go. So I want to find the rational roots. Now, first of all, if you tried finding the roots of this thing by factoring, you would not be able to. The grouping method or the box method won't actually work. But there's still roots. Some just don't factor. Okay? So, here we go. How we do it then is this. Is first of all, we make a list of all the factors of our last term. So my last term is 6. So what are some numbers that go into, Andy? What are some numbers that go into 6, starting from smallest to biggest?
1 and 6.
1, 2, 3.
4, 5, 6, 7, 8.
Well, just 6. 4 and 5 don't divide into 6. All right. So now my first coefficient, though, is 1. So that's easy. What numbers divide into 1? Just 1. We're good. Okay. Now, now what we're going to do is we're going to do all of our possibilities. First over last. So it could be 1 over 1. It could be, oh, I wrote this backwards, you guys. It's supposed to be last over first. Thank you for that encouragement. 3 over 1 and 6 over 1. Now, reduce them if you can. So this is 1, 2, 3, 6. It's actually just the same thing as all the last ones because our denominator was 1. And you also don't want to forget that we don't know the signs. They could be pluses or minuses. So here's the thing. I have 8 possible roots. It could be positive 1 or negative 1. Positive 2 or negative 2. Positive 3 or negative 3. Positive 6 or negative 6. How do I know which ones work? We're going to plug it in and see which ones make the polynomial equal 0. And that's where our calculators are going to come to rescue us a little bit. Now, you always want to start off with the easier ones. So let's start off with 1. So I'm just going to write this. I'm not going to plug it in here. So I'm just going to show my work on a calculator. Ready? So take your calculator and let's type it. So we have x cubed, right? So let's put parentheses 1 to the power of 3. What's next? 4x squared. So plus 4 parentheses 1.
You're going a little too fast. We all got different calculators.
Okay.
Wow.
I'm just typing it in.
Mr. Bailey, you're scaring me.
And then
You should have seen it yesterday.
okay, so I finished typing mine in, but if you need a second, I'll wait for you. Your power button is this little caret button here is what it's called. It doesn't look the same? Really?
Well, it's like everything's shifting.
Yeah, yes. Windows smaller, huh?
Or did you get the numbers?
Okay, so x cubed plus 4x squared plus x, and I'm plugging in 1.
Is that a negative 6 or a minus 6? I'll put a minus 6.
I'm plugging in 1 is all I'm doing, guys. And then I put it in my calculator.
Okay.
And then you push equals. What do we get?
0.
Guess what that means about 1?
Which one?
Wait a minute.
Was that a positive one?
Yes, it was.
So a positive one is a check.
So that was a root.
So we're done.
How many roots can this thing possibly have?
3 only.
It can have up to 3. Now, remember, this strategy can only find you the rational roots. But we'll keep looking. Let's see if we can find another one. Let's try negative 1. All right, now you could retype the whole thing if you want. So here we go. Parentheses. And don't forget, there's a difference between the minus button and the negative button. We want negative 1. Parentheses cubed. So that's plugging in negative 1 for x cubed. Plus 4 x, which is negative 1, to the power of 2.
No.
Plus negative 1 minus 6.
No.
Now, did that make 0?
Nope,
So-
we didn't.
There's only 2 left.
So that is not a root. Okay? Now I don't want to spend too much more time looking for roots here.
I don't either.
Um,
I thought it was weird.
the point is plug your numbers in, use your calculator to get the answer. Or you can just do it all by hand if you want, I don't care. But the point is it's supposed to come out to equal 0, right? And for the ones that are 0, that's your roots. What I do want you guys to do is I'd like you to do the first few steps here where you find your factors of your last term, factors of your first, find your possible roots, and see if you can find at least one root of the following polynomial. Okay?
Student practice.
There you go. Let's see what you guys have gotten. So, Sophia, what are the factors of my last term?
Sorry.
Hey guys, can you please be quiet? I'm trying to talk to somebody. Go ahead. 1 and 3.
That's it, right?
That's it, yeah, 1 and 3. So, Demir, you're not allowed to sit over here anymore. Too distracting, buddy. So next time you're over here behind Gene for good, okay? All right, now we're going to talk to Ishmael. Ishmael, what are the factors of my first term? One is correct. So now I got to figure out what my possible roots are. So, Taekwon, what are my possible roots? What are my possible roots? Good. 1 over 1 or 3 over 1, and it's plus minus, plus minus. So we actually have 4 possible roots. Now, Carlos, how can I tell which one of these are actual roots? Isabella, how can we tell which one of these are actual roots? How can we tell which one of these are actual roots? Go ahead, Escobar. That's right. All right. It is. Who found some roots? Nobody. Good job, guys. All right. So we'll call it quits. We'll see you tomorrow for some factoring practice. All right.
Daily, wait. We need our daily dose of depression.
Yeah.
Oh crap! I forgot.
I think a couple of you guys